This is the Proton Guru video practice for topic 1.5. These problems will give you practice on learning the arrow pushing formalism, or the curved arrow mechanism drawing that will be a really difficult topic for a lot of people in an introductory organic chemistry class. Some brief and straightforward reading to get you ready for these types of problems can be found in the Organic Chemistry 1 Primer 2018 in lesson 1.5. And you can also find additional chemistry videos and information on how to match up these videos to your particular course's textbook at protonguru.com. One type of problem using the arrow pushing formalism is, given a set of curved arrows, you're asked to provide the major product or products of the arrow pushing reaction shown. A really good way to start this type of problem is to identify any bonds that are made and broken in the product. So you draw dotted lines, for example, to indicate where a new bond should be in your product and cross out bonds that might be broken. In this case, we're taking a lone pair from the O and sharing it with hydrogen. And remember, the definition of a covalent bond is sharing of a pair of electrons, so we should get a pair of electrons shared there to make a new bond between the oxygen and the hydrogen. And now we should be able to draw in the product structure having just that new bond formed. And if you think about it, the two electrons in this bond used to be a lone pair in this oxygen. Now they're shared between the oxygen and the hydrogen. Now the last thing we have to do, since we're moving electrons around, is to check for changes in the formal charge. This hydrogen used to be positive in the starting material, and now you've given electrons to it, so it should be neutral. The oxygen, on the other hand, started out being neutral, and now it's shared electrons with the hydrogen. So if you look at the oxygen with a valence of 6 and take away the number of bonds, the number of non-bonding electrons, you see the formal charge in oxygen should be +1, indicated here. And you've got to show all the non-zero formal charges in these types of problems to get the correct product. So we'll do a few more of these in this video, and the procedure you'll want to follow is to assess which bonds should be made and broken on going from the starting material to product. Add some visual markers to remind you about this so that when you draw your product it's a little easier. And then you can fill in the product structure, having all the new bonds that you made, like in this case, but missing the bonds that are broken. And then check the formal charges of any atoms that were involved in changes in bonding. So let's apply these techniques to this next problem. Take a look at this arrow that's provided for us. It shows we're taking two electrons out of this space and dumping them onto the oxygen. So if we mark the bonds that we made are broken, we could say, well, this bond's going to be broken because we're taking the two electrons out of that space, and two electrons are a bond. And now if we draw those same atoms without the formal charges, and you see we're now missing that bond that used to be here because we took the electrons out of that space, we see that we have two fragments. And the last thing we have to do is check for formal charges. One really tricky thing in these types of problems that confuse a lot of students in the introductory class is if you have a carbon in a line bond structure like this, remember that you don't have all the hydrogens shown to you. A carbon with 4 bonds has a different formal charge than a carbon with 1 or 2 or 3 bonds, so you have to draw in all the missing hydrogens. Now most of these carbons didn't change their bonding. We didn't add or take away any bonds from this, or this carbon, but the carbon here that was attached to the oxygen had a change in bonding, so its formal charge might change as well. So let's look at that more carefully. In the line bond structure, we don't have to show the hydrogen, but we need to know it's there in order to get the correct formal charge. So to start, we know that there's no formal charge. Formal charge is 0 on that carbon, and that's the usual neutral carbon with 4 bonds and no lone pairs. We get that information from the Lewis symbol. Here, at the end, we've taken one of the bonds away, and those two electrons went onto the oxygen. Now the oxygen has a formal charge of 0, 6 minus 2 bonds minus 4 non-bonding equals 0, if you remember the formal charge equation. But for the carbon, you see that there are only 3 bonds to the carbon. Carbon with 3 bonds and no lone pairs is missing that 4th electron. So missing 1 electron makes it +1. You can also solve it by saying the valence of carbon is 4. Take away the 3 bonds, take away no non-bonding electrons, there aren't any lone pairs, you get a +1 formal charge for that carbon. Now let's apply the same procedure to another problem. Provide the major products here. Well, we're first going to want to mark which bonds are made or broken. We see that we're taking electrons away from the space between the hydrogen and the carbon, so that bond won't be there anymore. We're dumping the 2 electrons into this space, so we're trying to make a second bond between the 2 carbons here and here. So if we annotate that by crossing out the bond that breaks and drawing a little dotted line to remind us that's where a new bond has to go in our product, we should be able to draw the fragments we get from this movement of electrons. So here's the bond we made, And we used to have a bond here, but that's gone now because we took the electrons out of that space. Now we have the two fragments and we have to add formal charge. So if we take a look at the hydrogen, this hydrogen lost its 2 electrons that it had in the share of this bond. Now you have a hydrogen with no electrons around it. So hydrogen atom that's neutral has 1 electron. You've taken all the electrons away, so you get H with no electrons has a positive charge. On the other hand, the carbon that used to be positive now has 4 bonds. And that's the standard neutral usual way for a carbon to look. Let's take a look at another problem like this. And here we see this bromide donating a pair of electrons to this carbon with a cationic charge on it. So we should be sharing a pair of electrons from bromine to carbon. That should be making a bond there. If we think about marking the bonds to be made or broken, we say, well, we should make a new bond there where I have that dotted red line. We don't have any arrows indicating a breakage of bonds, so that should be the only thing that happens. So we'll draw the structure again. We have the same carbon backbone, but there's our new bond between the bromine and the carbon. And now we have to think about formal charges. One thing about the formal charges is that you might need to know how many lone pairs there were to start in order to know how many are in the product. If you look at the starting material, it had a Br minus in it. If you think about bromine and its Lewis symbol, bromine is in the 7th tall column of the periodic table. So without any charge on it, your bromine atom has a Lewis symbol with 7 electrons. If I have to add an electron, that's where I put an extra electron and get a negative charge. So the bromine started out with 8 electrons, and now it's taken a pair and used them right here to make this bond. So that pair is sitting there shared with carbon now. Now I can figure out the formal charge on the bromine. The valence was 7. Take away the number of bonds, and then take away the number of non-bonding electrons. There are 3 lone pairs, 2, 4, 6 electrons. Now there's a charge of 0 on the bromine. The carbon started out with a positive charge. Because a carbon that's neutral has 4 bonds, I take away one of those electrons and it's positive, it has 3 bonds. But in the product, it has 4 bonds, which is the usual state for a nice neutral carbon in a structure. Let's do one more of these. Here's a little bit more complicated of a case. We have 2 arrows, so that when we go to mark which bonds are made and broken, we see that there's a sharing of electrons from this bromine to this carbon. We should make a new bond that way. And there's also, at the same time, taking these 2 electrons away and pushing them onto the oxygen so that bond should break. So if we mark those, we're going to make and break a bond at the same time. That allows us to figure out what fragments we have at the end. Now we need to figure out what charges we have. Remember that we have a line bond structure for the carbons here. We have to figure out how many hydrogens we had to start. This carbon was neutral in the starting material as indicated by no charge being drawn on that carbon. And that's how you know it had 4 bonds. That's what carbon does in a normal neutral situation. So there is a hydrogen there. That hydrogen doesn't go away in our product. It's drawn a little bit of a weird geometry, but it'll allow us to figure out the formal charge. The carbon still has 4 single bonds. Carbon has a formal charge of 0. You can check the oxygen. It used to have a positive charge, and remember that it gained electrons in the arrow pushing we had. And now it has 2 lone pairs and 2 bonds. And if you think about the Lewis symbol for oxygen, it should have 2 lone pairs and 2 bonds in a neutral usual state. Well, we've done a bunch of problems where we're shown arrows and we're asked to figure out the products. Now, what if we have both the starting materials and the products provided to us, and instead we are asked to provide the arrows to figure out how the electrons had to move to accomplish that given transformation? Well, the procedure is sort of the reverse of what we did when we knew what the arrows were. So we again have to mark what bonds we need to make and what bonds we need to break on each side of the equation. So let's start on the reactant side and see which bonds we had in the reactants but that we no longer have in the products, and we'll mark those. Well, we don't have this 3-membered ring having the oxygen in it anymore, so that bond has to be broken. And in the product, we see that the OCH3 unit that started out being not attached to the other part is now attached. So this is the bond we made, and this is the bond we broke. Next, let's note which atoms need to give electrons away and which atoms need to gain electrons. And we can most easily do this probably by looking at the charges. If we look at the starting material, this O with the CH3 on it starts off being negative. but in the product it's neutral and bound to the carbon. It's going to have to give electrons away so that it won't be negative anymore in the product. On the flip side of that, you see that in the product, this oxygen that is attached to this carbon here is negative, and that's this oxygen. It's going to need to gain some electrons to get that negative charge. There's only going to be one way to draw arrows from bonds that are broken to places where bonds are made, while drawing arrows away from atoms that need to lose electrons and to atoms that need to gain electrons. So here we see the correct arrow pushing mechanism, the curved arrow shown by these two arrows. We need to lose this bond. This bond has to break for the product. We need electrons on this oxygen. That's how we know that the arrow points in that direction. This oxygen needs to be the one that gains the electrons. We also need to make the bond from this oxygen, which is here, to this carbon, which is here. And this atom has to lose electrons, so that's how we know that this is what's giving the electrons, and the carbon would then be what is accepting the electrons. And by drawing this particular arrow pushing mechanism, we get the correct product. Now the procedure is to figure out which bonds need to be made on the product side, which bonds in the reactant side will break, note which atoms need to gain and lose electrons, and then add all the arrows. Make sure that you're pulling electrons out of the bonds that are broken, pushing them into the spaces where you need new bonds. Be sure that you're giving electrons to the atoms that need to gain negative charge, and make sure you're taking electrons away from atoms that need to get rid of electrons. So let's apply this procedure again to this problem. Provide the curved arrows needed to transform this alkene into this cationic species. So we again start off by marking bonds that are made and broken. Well, we don't have a double bond in the product, so we've got to get rid of that somehow. And what we have is this proton that was floating around as a separate entity is now attached to this carbon on this side. So that's a bond we need to make with our arrows. Next, we figure out which atoms need to lose electrons and which need to gain electrons. In this case, this carbon atom that was in that alkene started out as neutral, but over in the product you can see it's cationic, so it needs to get rid of its share of some electrons. So get rid of some share it has of electrons in these bonds. On the other hand, the hydrogen started off being positive, that's a proton. It needs to gain electrons because in the product here, it's neutral. It's no longer got that plus charge. So now we draw our arrows. If this needs electrons and we have to get rid of these electrons to break that bond, there's really only one arrow we can draw for that. If we do that, it leaves the carbon on the left with only 3 bonds. A carbon with only 3 bonds has a +1 formal charge, which is shown in the product already. Here's the new bond we made. That used to be the electrons that were in this double bond. And now we have the correct arrow pushing for this step. So let's do one more involving some anion reacting with a neutral compound. We'll start off by marking the bonds to be made and broken. We see that, for example, the hydrogen attached to the carbon isn't there anymore. This carbon just has a lone pair. And we figure out that the carbon starts out neutral, it ends up anionic, it needs to gain electrons. Meanwhile, this nitrogen starts off negative and it becomes neutral, so it needs to get rid of some of those electrons that make it negative. We also see that the nitrogen in the product has 3 hydrogens, but in the starting material it only has 2. So it needs to gain that hydrogen by making a nitrogen-hydrogen bond. If we consider all of those factors, we see that, well, the NH2 unit needs to lose electrons, right? And it needs to bond to a hydrogen. So that's how we figure out that that arrow is needed. We also need to get rid of this bond. It's not present in the product. And the fact that the carbon needs to gain electrons to become negative over here, that tells us that those electrons have to go towards that carbon rather than away from it. And that's our correct arrow pushing for that step.